All right, plan for this recording is to talk through the 7.1 notes. We're probably going to do the two different sections, not probably, we're going to do two different sections, 7.1 and 7.2. 7.1 is pretty straightforward, pretty short. 7.2, not so much. 7.2 is going to be where we spend most of our time today. So let's get rolling. The first thing we're looking at in 7.1, this idea of two variables being directly related or varying directly. So the equation at the top, if two functions or two variables have a direct variation relationship, then it'll be y equals k, some constant, times x. And the way you read that, or the way you say that, is y varies directly with x. If two functions are inversely related, you can see that two functions are combined variation. That means it has both direct and inverse. So y varies directly with x and inversely, with v. And like I said down there, k is my constant of variation. It's how they vary, how they relate to each other. Okay, so question number one. Y varies inversely with x. First step, write that in a general equation. Well, we just did that right here. Inverse variation says y is equal to k over x. Let me get rid of this guy here. So we have y equals k divided by x. I'm going to change that a little thinner. Okay, and now I'm going to plug in my value for x and y. So 1 is my value for y, k is what I need to find, and my value for x is 4. Okay, so put 1 in for y, and I put 4 in for x into my generic y varies inversely with x equation. K is my constant, is how they relate. So I multiply both sides by 4 to get k by itself. And k equals 4, because on the right-hand side, my 4's cancel. On the left-hand side, 1 times 4 is 4. So my final equation, y equals 4 divided by x. Now, if you were looking at a table of values, and the question asks, is this direct variation, is it inverse variation, and so on, I don't know, 1, 2, 3, 4. Notice that if I multiply both sides by x, then whatever x and y are, if they are inversely related, they have to multiply together to equal this constant, this 4. So this would be like 4, this would be like 2, this would be whatever it needs to be. What would that be? 4/3. This would be a 1, that's a 3. To get the idea? So if you have two variables that are inversely related, when you multiply them together, any two combinations of x and y should multiply together to give me that constant, whatever that constant is. And I see that because I multiply both sides by x, and I get x times y has to equal 4. Okay, that was a side note. In the textbook, we do have some homework problems where, well, if we were to do the textbook homework problems, we would have some where they ask you that question right there, but we're not going to do them. All right, question B. Now, using this equation, find the value of y when x is 7. So I plug in 7. I plug in 7 for x, and I'm done. Y equals 4 divided by 7. Okay, question 2. U varies directly with n. What does that look like? Direct variation. Y equals k times x this time. So in this case, it'd be u varies directly. So u equals k times n. U varies directly with n. Y varies directly with x. This is my generic relationship. This variable varies directly with this variable. So this variable is equal to some constant times X. Real life situation. You go to the gas station and you put in gas in your car. The amount you pay is directly related to the number of gallons you put in. How is it related? By the price per gallon. So we're creeping up on $4 per gallon, so Y equals 4 times X. Real life situation where Y varies directly with X. So use my two variables given. U is 27. So I put 27 in for U. N is 9, so I put 9 in for N from right there. Divide both sides by 9, and the relationship between U and N is 3, so K equals 3. So 3 times N is equal to U. And that's my equation. Write your generic equation, plug in the information they tell you, solve for K, plug the K value back into my generic equation. Now question B, use the equation from part A. U is 11, and solve for N. Divide both sides by 3. So N equals 11 divided by 3. And we're done. Number 3, P varies directly with W. P equals K times W, but inversely with Q. So it's K divided by Q. I don't need two different K values because P is related to both W and Q using the same constant of variation. Okay, plug in 22 for P. Plug in 3 for W. Plug in 4 for Q. Do a little solving. I multiply both sides by 4. Divide both sides by 3. And my K equals 88 divided by 3. Go back to my first equation. P equals 88 divided by 3W over Q. Now in here, this could say P varies directly with W squared, and they need to put a squared up here. And inversely with Q to the third power, or whatever they say, then you just plug in that exponent depending upon what they tell you. In this case, it was just W and just Q. Okay, I'm going to tweak this a little bit. Why? I'm not supposed to have fractions inside of a fraction, so I'm going to multiply top and bottom by 3 in order to get this fraction to go away. And my equation is going to be P equals 88W over 3Q. Multiplying by this by 3 makes the fraction go away, which is what I wanted, and then it's just 3 times Q. I multiplied top and bottom by the same value, so I really just multiplied by 1. Multiplying by 1, we know, does not change the value of my fraction. It just changes what it looks like. Okay, plug in my information. P is 50. W I don't know. And Q is 9. Work it all out. I get 9 multiplies together. Was that 27? Whoops, I don't need an equal sign there. So I get 50 equals 88 divided by 27. There's a W on top. I'll multiply by 27, and then I'll divide by 88. I'm going to go ahead and go to a decimal. And I get 15. Whoops. I get 15.34. Multiplied by 27, that goes away. And I divided by 88, and I just did it all in one step. I get 15.34. And there's W. All right. That is inverse and direct variation. I won't say now the hard stuff, now the fun stuff. I'm not going to read all these, but I am going to refer back to them. So you may want to hit pause and read these definitions, what the x-intercept is, what the y-intercept is. You have them on your notes also. Read all of these definitions. Do more than read them. Read them and try to kind of understand them. The hole and the slant asymptote are going to be two things that we're going to talk about in a little more detail. And the slant asymptote, we're really not going to do much of this year, but I want you to see it. And we're going to do a lot more next year in pre-calc. But this year, we're not going to do a slant asymptote. I do have one on the homework just because I want some of you to see it. All right. Question number 1. The most basic rational function. So let's define that word rational. Some of you know, back from whenever you heard the word a rational number, is a number you can write as a fraction, in fraction form. So a rational function is a function that's in fraction form. So my most basic one, y equals 1 over x. Cruising back up here, x-intercepts, value of y that make the numerator, the top of the fraction, equal to 0. What makes 1 0? What value for x makes 1 0? Well, there isn't one. It's 1. So there are no x-intercepts. Y-intercept, the value of y when x is 0. All right, let's plug in 0 for x. Well, I can't. 1 divided by 0, not possible. So there are no y-intercepts. Vertical asymptotes, value for x that makes the bottom 0. Well, that'd be x equals 0 because it's just an x down there. And here's a tough one, horizontal asymptotes. So we have 3 options. We are going to look at the degree of the top compared to the degree of the bottom. So let's go back to chapter 3, polynomials. I think it was chapter 3. A degree of a polynomial, the degree of the top, is the largest exponent of the top. The degree of the bottom would be the largest exponent of the bottom. So in this case, the degree of the top is 0 because there isn't an x up here. The degree of the bottom is a 1 because that's a 1 right there. That's a 1 right there. Okay, so the degree of the bottom is bigger than the top. The degree of the bottom is bigger than the top. Okay, so let me read through my options. If the degree of the top is greater, nope. If the degree of the bottom, nope. If the degree of the top is less, there we go. The bottom's bigger, which means the top's less. So here's what I'm looking at. If the degree of the top is less than the degree of the bottom, the horizontal asymptote is y equals 0. That's what I have. This is a situation that I'm looking at. The top is smaller than the bottom. In case you keep seeing me pause the video, I still have a cold. I'm still coughing like crazy. So instead of you hearing me cough, I keep hitting pause. All right. So my horizontal asymptote is cruising across here at y equals 0. My vertical asymptote is cruising down here at x equals 0, right? So these are my 2 asymptotes. Let's go back to the definition of an asymptote. Back in exponential and logarithmic functions, I defined this very clearly, very carefully also. Vertical asymptotes, your lines will never cross a vertical asymptote, okay? But your horizontal asymptotes is the y value your graph approaches when x goes to negative infinity or positive infinity. And it can cross, your graph can cross a horizontal asymptote as many times as it wants to. But as you get closer to infinity, way out there, your graph is going to go to the y, or in this case, the x-axis. My graph could do this number. My graph could go like this, and then it could go to 0. Okay? Most likely it's not going to, but it can cross in this region in here. Okay, horizontal asymptote, we said was y equals 0. There's no slant asymptote. If there's a horizontal, there won't be a slant. And a hole, there's no hole. We'll talk about that later. Okay, let's get your graph. So now let's look at some points. If x is positive, so I'm going to look at this region over here. Okay, so here's my vertical asymptote. I need to say that also. Vertical asymptotes divides your graph into different regions. If you have one vertical asymptote, you'll have two parts to your graph, one on this side, one on this side. If we have two vertical asymptotes, you'll have three parts to your graph. If you have four vertical asymptotes, you'll have five parts, and so on. You always have one more part than you have asymptotes, vertical asymptotes. So what happens out in this region to the right of this vertical asymptote? What happens to this graph? Well, x is positive, right? So 1 divided by a positive number will be positive. So I know my graph is up here. One more time. When x is to the right, so what happens out here to the right of this asymptote? My values out here are positive x values. So if x is a positive, 1 divided by a positive value will be positive. So I know my graph is out here. Okay. Where is it out there? Well, I just plugged in one value. When x is 2, y is a half. When x is 1, y is 1. And we're not going to always plot points, but for this one we can. If x is a half, y is 2, and so on. What happens to this fraction as x gets really big? So 1 divided by 2 is a half. What's 1 divided by 20? Well, it's pretty small. 1 divided by 200. Well, it's even smaller. 1 divided by 2,000. Well, it's even smaller. So like we said, as x gets big, as x goes to infinity, y is going to go to 0. So this graph is going to come down, pass through those points, and flatten out and approach 0. Okay, what happens as x gets close to 0? What if x is a half? What's 1 divided by a half? Well, when you divide by a fraction, you multiply by the reciprocal, so it's 2. What's 1 divided by a 20th? Well, that'd be 20. And you get the idea. 1 divided by 1 over 2,000 is 2,000. So as x gets small, y explodes to infinity. We have a vertical asymptote. As I get close to the asymptote, it's not going to hit it. It's just going to explode and go up alongside of it. Okay, on the other side, what happens if x is equal to a negative 1? Well, if x is a negative 1, then 1 divided by negative 1 is a negative 1. If x is negative 2, it's a negative half. If x is a negative half, it's a negative 2. And we get the same looking shape, just on the negative side. So it comes like this. It comes like this. And flattens out. And it doesn't cross this one. It flattens right up next to it. Whoops. Right up next to it. I do have arrows on the end of those. May not look like it, but I do. Okay, so there's my graph of y equals 1 over x. Okay, number 2. See if you can hit pause and at least answer these questions. You may not be able to graph it. I don't expect you to be able to graph it. See if you can answer these questions based upon the definition. Okay, either you're back or you never left and you just want me to keep going. X-intercepts. I'm not going to go back up there. I know the definitions, so you can look at them if you need to. X-intercepts. Value of x that makes the top or the numerator 0. So my x-intercepts are x equals 0. So I have 1 point at 0, 0. There's one x-intercept. Any more? Nope. There's just one value of x that makes the top 0. Y-intercept. Put in 0 for x. So I get 0 divided by, well, 0 divided by anything is 0, other than 0. And that's not going to be 0. So my y-intercept and my x-intercept are at the same point. All right, that's okay. Vertical asymptotes. Value for x that makes the bottom 0. Well, what makes that 0? 1. So I have one vertical asymptote at x equals 1 and negative 2. I have another vertical asymptote at x equals negative 2. Horizontal asymptotes. The degree of the top compared to the bottom. What do I have? The degree of the top is 1. The degree of the bottom. If you were to multiply this out, you would get x squared, yada, yada, yada. Which is bigger, a 2 or a 1? Well, the bottom is bigger than the top, so my horizontal asymptote is again at y equals 0. The degree of the top is a 1. If I multiply these two x's together, I get an x squared, which will be the highest exponent. So my degree of the bottom is a 2. 1 is smaller than 2. So my horizontal asymptote is y equals 0. And there's no slant asymptote, and there's no hole. Okay, let's sketch a graph for this thing. X-intercept 0, 0, we did. Y-intercept 0, 0, we did. -2 is one vertical asymptote. So I have a vertical asymptote cruising down here. Sorry, drawing a straight line down for some reason on this tablet's not easy. And 1. All right, next thing, horizontal asymptote. Horizontals are easy to draw for some reason. Is y equals 0. Now, and on this one, I'm not going to plot points like I did on the other one. All I'm going to do is care about where it's at. So I have 3 regions. I have 2 vertical asymptotes, so I have 1, 2, 3 different parts to my graph. I have 2 vertical asymptotes, so I'm going to have a part of a graph over here, a part of a graph here, and part of a graph here. And all 3 parts makes up the graph of this rational function. So ask ourselves the question, when x is greater than 1, okay, I'm looking at all my values over here. When x is greater than 1, is my graph positive or is my graph negative? Let me ask you one more question. Does my graph ever hit the x-axis over here? No, it only hits right there. So if x is positive, rephrase that. If x makes my graph positive, anywhere over here, it will stay positive the entire time. Since my graph never passes through the x-axis, if I plug in the x value in that's greater than 1 and I get a positive value for the function, that means my function is always going to be positive over here. And vice versa. If I plug in a negative, it will always be negative because it never passes through 0. And the only way to get from up here to down here is to go through the x-axis, and it never does. Okay? All right, so plugging in a number bigger than 1. How about 2? Putting in 2 on top gives me a positive number on top. Putting in 2 into x minus 1. 2 minus 1 is positive, right? 2 plus 2 is positive, right? So, a positive divided by a positive will always be positive. And since I know my graph approaches this asymptote, it comes like this. That's not there technically. I know my graph comes down like this. And here's where I don't care. I don't care where it turns. Okay, at some point in time, maybe next year in pre-calc, we do care. We're going to come down like this. We're going to curve, and we're going to approach that asymptote. How do I know? Because it has to. As x gets close to this asymptote, I know it goes to infinity, because that's what a vertical asymptote does. As x gets really big, I know it goes to 0, because that's what a horizontal asymptote does. I know it never crosses this asymptote because my only x-intercept is at 0, 0, right there. It can't do anything other than that. You may ask, well, why doesn't it do this? Because I know it doesn't, because it's not a polynomial function down here. It's just a y equals x squared, and it's just going to come down and approach the asymptote. It'll look just like that. Okay. Next thing. In between 1 and -2. What's between 1 and -2? Well, I don't want to plug in 0 because I already know that's 0. How about in between 0 and 1? How about a half? My question is it up here or is it down here? When I plug in a half into the top I get a positive, right? Because it's a positive half, so I get a positive. Plugging in 1/2 right here, a half minus 1, that's not positive. That's negative. Plugging in 1/2 right here, a half plus 2.5 is positive. So I know my graph is a positive divided by a negative. I know my graph is going to be down here. So it has to approach the asymptote. So it comes along the asymptote. And then it passes through. Man, this is going to be hard on this tablet. It passes through that point. It can't turn and come back down. Why can't it turn and come back down? Because it can't pass through the x-axis any other place than right there. That's my only x-intercept. So it has to just keep on going towards that asymptote. And it approaches that asymptote and goes to infinity. And there's my middle section. As you notice, my graphs have to approach vertical asymptotes. They'll come right as my x values get close to it. It's going to explode to negative infinity, or it's going to explode to positive infinity. Here's a big statement. My graph will be on opposite sides of that asymptote. Rephrase that. When I look at the graph on the opposite sides of the same asymptote, so at x equals 1, if on the right-hand side it goes to positive infinity, then on the left-hand side it will go to negative infinity. Unless the factor that gives me the vertical asymptote is squared. Had this x plus 1 been squared, then my graph would stay on the same side of the asymptote. But it doesn't. In this case, since my factors are not squared, if it goes to positive infinity on this side, it'll go to negative infinity on this side. Well, let me use that to help myself then. On this side, it goes to positive infinity. Then on this side, it'll go to negative infinity. It's going to come from here. Now, I know it doesn't cross this, right? We've already said that many, many times. It only crosses there, so it has to come up and go to that asymptote and go to 0. And there's my graph of that function. So the hardest part, obviously, is the graph. This stuff here, pretty easy. Drawing them on there, pretty easy. Hardest part is figuring out where this all is at. And I get it. It's going to take some practice. Okay, question 3. See if you can fill out all of this stuff. There's no slantote, asymptote, and there's no holes. We're going to get to that later. So just fill out these top 4 parts. Hit pause, see if you can do that. Okay, I assume you hit pause. So what makes x minus 2 0? 2. When will this be 0 when x is 2? When will this be 0 when x is a negative 1? So I have x-intercepts at positive 2 and negative 1. Y-intercept, put in 0 for x. So I get negative 2 times a positive 1 over a negative 3 times a negative 1. On top is a negative 2. On bottom is a positive 3. And I get a negative 2/3. So my y-intercept is negative 2/3. So 0, negative 2/3. And I simply just plugged in a 0 for all of my x's. Okay. That's going to go away. We don't need this up here either. Kind of distracting. All right. Vertical asymptotes. Values for x that make the bottom 0. So x equals 3 and x equals 1. Notice my notation. Being careful on my notation. X-intercepts are xy coordinates. The x is some number, the y value is 0. The vertical asymptotes are x equals a number. They are equations. They're lines. Okay, so when x is 1 and when x is 3. Okay, there's my vertical asymptotes. Horizontal asymptote, degree of the top. If I multiply that out, I get x squared on top. Yada, yada, yada. Don't care about that up there. I get x squared on the bottom. We have a different one now. Let's cruise back up here. The degree of the top is the same, right? X squared, x squared. The degree of the top is 2. The degree of the bottom is 2. Cruise back up to our notes. If the degree of the top is greater, not. If the degree of the top is less, it's not. If the degree of the top is the same, there we go, then it's the ratio of the leading coefficients. If the degree of the top and bottom are the same, my horizontal asymptote is y equals the ratio of the leading coefficients. Well, if my x squared terms are the first terms, there's a leading terms, my ratio is 1 to 1. So my horizontal asymptote is y equals 1 divided by 1, which is 1. That's probably going to be the hardest part, okay, is just trying to determine the horizontal asymptote. One of the hardest parts. Okay, so I have a horizontal asymptote cruising across here at y equals 1. I have x-intercepts there, I have x-intercepts there, and so on. All right, here we go. I have 2 vertical asymptotes. I'm going to have 1, 2, 3 different graphs, parts of graphs. Same question. It never crosses the x-axis down here. So I'm just going to jump out here and say, I know it can't do this. It can't approach this asymptote and approach this asymptote because that would require it to go through the x-axis. And it doesn't. So right away, I know where it's at. I know it's up here. One more time. My graph has to approach this asymptote. It has to approach this asymptote. If it came from, I'm just saying if it came from this down here, it would have to pass through the x-axis in order to get to this asymptote. So I know it can't come from the bottom and go to the horizontal asymptote. That would require it going through the x-axis. And the only 2 places it crosses the x-axis are in these 2 places right here. So I know it can't be up here. It has to be here. And again, if you drew it out here, or if you drew it in tighter, I don't care. Okay, we just want to kind of know where is the general shape of my graph, and it's out over in here somewhere. Next year in pre-calc, we'll get a little more picky about where it's at. We're just looking for just seeing basic rational functions. Well, no, they're not basic rational functions, but the basic shapes. I'm going to use my trick. I know that if it goes to positive infinity on this side of the asymptote, when I go to this side of the asymptote, it has to be down here. So it has to come from here, which makes sense. It has to cruise up here, pass through that point right there, and then approach this asymptote on this side. Whoops, and approach this asymptote on this side. Let me smooth that out a little bit. That was horrible. So it comes from here, passes through that guy, and on down. Wow, and on down. Why is it so hard to draw a straight line to that asymptote? And they're not supposed to have all those little wiggles in there. All right, I got to be able to draw a smooth line with this thing. I don't know why it's so hard. These Wacom tablets are supposed to be really easy to draw, but they're not to draw on. If I go fast, maybe if I just go fast. All right, that's better. All right, there we go. Sorry, I'm talking to myself in my room. So next thing, we have those points there. If it starts on the, if it's on the top on the right-hand side, it has to be on the bottom when I go to the left. So it's going to come from here, and it's going to go up, pass through those 2 points, and approach this. I think I can draw better going this way. So it cruises here, passes through that, passes through that, and approaches that asymptote as I cruise down. It has to. It can't be up here, because I'd have to go through that point, and then go back to here, and it has to come from here, pass through that point, and approach that asymptote. The more you do these, the more comfortable you're going to get seeing where they go. Okay, The only difference on your worksheet is you're going to be given equations where you have to factor first. I don't know. Oh, that'll give me a hole. Whoa, way too big. What do you want? 12? All right. So you're going to get you're going to be given stuff like this. Just factor. Factor the top to look like that, factor the bottom to look like that, and then you can find all your different stuff. Okay. On the homework worksheet, there's another recording called Rational Functions Graphing Worksheet, and I talk through every single one of them. Here's my, not requirement, here's my suggestion, strong suggestion. Try them first before you watch the recording. The hardest part is getting comfortable doing this graphing part. If you never make the attempt, you're not going to get better. Make an attempt, even if it looks silly. Okay? Make an attempt, and then you can check your logic. I talk through how to graph it, what to look for. Okay, so there's going to be another recording then where I talk through every single question. Okay. Hope that helps, and move on. Ask the sub for the next homework worksheet if it has not been given to you already, and then get going on it. Okay.